Een hele goede middag iedereen. Welkom bij de webinar Betere uitkomst door de nieuwe generatie calculatieformules. Wij organiseren deze webinar in samenwerking met Haagstrijd, producent van onder andere de Landstar. En de vraag is natuurlijk, wat kunt u de komende 50 minuten van ons verwachten? Nou, zoals we weten gaat het over biometrie. De volgende onderwerpen zullen de revue passeren. Namelijk, wat doen IOL-formules? Welke formules zijn er? En wat zijn de ontwikkelingen, bijvoorbeeld de Barrett en de Old formule? En waarom T-cone bij torische IOL's? En hoe werkt de T-cone? Daarnaast T-cone platform. En na afloop heeft u de mogelijkheid om vragen te stellen. Wat betreft de vragen, verzoeken wij u vriendelijk deze vragen in Engels te stellen en bij voorkeur op het einde. Graag introduceer ik u hierbij de heer Thomas Beutler, product manager van Haagstrijd. En vanaf nu zal dan de voertaal dan ook Engels zijn. Wij wensen u een leerzame middag. Wat leuk is dat deze webinar morgen online te bekijken is op onze website www.ootech.nl. Dus www.ootech.nl. Thomas, it's your time.
Thank you very much, and I would like to welcome you here in the name of Haagstrijd for this unique webinar, and I would like to thank Laméris to provide me with the opportunity to talk to you on new means of IOL calculation formulae. So let's have a look what we do. First, we'll talk about IOL calculation in general. So what do IOL formulae do? The next topic is going to be the Olsen formula. And last but not least, we'll talk about torics, how we can calculate them, how we can get the best refractive result out there with the help of topography, the iSuite IOL toric planner, and the Barrett toric calculator, a new formula on the market. Okay, let's start with some basic introduction on what do IOL formulae do. So, when we do IOL calculation, we want to know what IOL power do I have to put into the eye to get the best refractive outcome for the patient? Well, we know that the IOL is going to sit in the capsular bag in an uneventful cataract surgery. So that's true. But where it exactly sits, that's the one thing which is the big mystery in all IOL calculation formulae. And that's where the formulae differ the most. So it's all about the effective lens position. Let's have a look how different IOL calculation formulae calculate the ELP. First of all, we have the standard two-variable formulae like Holiday 1, Hofer Q, and SRKT. They're still in widespread use, but they have some limitations. So the effective lens position, which is actually a virtual position, it's nothing you can measure. It's the principal plane of the IOL, is calculated with these three formulae based on axial length and K readings. So what they assume is that there is a linear relationship between axial length and the ELP and also between the K readings and the ELP. So for example, a very long eye in these formula will provide a deep ELP. A short eye on the opposite side will provide a shallow ELP. But if we look at the anatomy, we will see that short eyes not necessarily all have shallow anterior chambers. More often they actually show completely normal anterior chambers, and therefore these formulae tend to provide not the best result with extreme eyes on the long side as well as on the short side. The same is true with the K readings. A steep K does not necessarily lead to a very deep anterior chamber, and flat Ks also not necessarily to a shallow one. And that's the limitation we have here. Next formula I would like to look at is actually the Huygens formula. Huygens went beyond that. He introduced ACD measurement within IOL calculation. He still has axial length K readings, but in addition ACD. And his ELP prediction is only dependent on ACD measurement and axial length. That's the reason why Huygens formulae performs a little better than all the other formulae, because he predicts the ELP on a parameter which is actually 100% tied to the lens position, and that's the anterior chamber depth measured. And here, that's where newest formulae like Holiday, 2, Olsen, and Barrett go beyond, because they add more parameters to the calculation of the effective lens position. We have Holiday 2, which is widespread use in the States. He's using axial length, K readings, anterior chamber depth, white to white, lens thickness, age, refraction, shoe size, zodiac sign. Oh, no, sorry, those are not there. Anyhow, so he's using up to 7 parameters to calculate the lens position and then the power. Now you might wonder, why is he using so many parameters to calculate the IOL power? Basically, the reason for this is a lot of the devices out there don't provide all of the parameters. There are not too many optical biometers out there that provide lens thickness, for example, and there the Holiday 2 formula replaces the lens thickness parameter with age and uses a simple age-based formula to derive an lens thickness. When Olsen first started, he basically used as many parameters as Holiday, but what Olsen did is he boiled the whole thing down to the parameters that are really necessary to calculate accurate IOL power. And that's the axial length, the K readings, the ACD, and the lens thickness. And he stuck to those parameters because they are now available at high accuracy with the lens star. Barrett, on the other hand, is also using the same set, but also white on white. So let's focus on Olsen first. This is Professor Olsen, and let's have a look at his formula. So as said before, Olsen is using 4 parameters: axial length, K readings, like everybody else, ACD, and lens thickness. His way of calculating the IOL differs completely from all the others. All the other formulae are so-called thin lens formulae, so they assume every refractive surface of the eye to be infinitely thin, and they only calculate in principal planes. That's why all the other formulae talk about an effective lens position, this virtual position of the effective lens plane. On contrast, Olsen is using ray tracing to calculate the lens power. So ray tracing actually simulates the path of the rays of light through the refractive media of the eye. And in there, he's using for the lens position a measurable parameter he's calling lens position. And this lens position is actually the summation of a measured anterior chamber depth, so from the corneal apex to the anterior capsular bag, plus C times the thickness of the crystalline lens. And this C is his C constant. Now let's have a look why he calls this the C constant. He actually did a large study on more than 1,000 eyes. That's on one lens, and what you see here is the plot of where the lens sits in the capsular bag plotted against the axial length. And you see that the position of the lens is always at 0.4 times the capsular bag size. And it's a true constant. You have some spread, but that's the normal way anatomic structures work when you try to describe them. If we look at the predicted lens position versus measured lens position with the lens star, we get a very nice correlation. We have R of 0.84. Some of you might say, well, if I look at mathematical formulae, 0.84 is not strong. But if you look at an anatomic structure, which we have here, 0.84 is a really strong correlation, and you will hardly find anything like this published in history. So, looking at this data, we can summarize the C constant is a true constant, and it might be regarded independent of axial length. It's also independent of the K readings, independent of age, independent of gender. So it really is a constant. And that is a different as compared to the other formulae like Holiday 1, like Hofer Q, like SRKT, also like Huygens, because their length constant depends on various parameters. We do provide you with a PDF file on the Olsen formula where you can actually have a little wrap-up, also featuring peer-reviewed data links to papers by Olsen and others. This will be available also tomorrow on the Laméris Ootech website, www.ootech.nl. Also, if you want to have a further look into this, you can visit the Hawk-Stride website, www.hawk-stride.ch or .com, and there you'll find a link to lunchtime webinar from the ESCRS. And in there we have different talks, and one talk focuses actually on the refractive outcome of Olsen. Let me quickly provide you with a wrap-up of this talk. It's a study done on almost 700 eyes where the outcome of different IOL calculation formulae were compared. It was based on Holiday 2, then it was compared to Olsen, but also to the standard formulae SRKT, Huygens, and Hofer Q. And here, let's have a look at the results. The bar diagram shows it the most impressive. The blue bars are patients within half a diopter, green within 1, and yellow within 2 diopters. So if we look at the blue bars only, we see that all the standard formulae, they provide results in the mid-70s to early 80% within half a diopter. That's what you expect in a practice that works with optimized IOL constants. If we look at Holiday 2 and Olsen, we'll see that they both go close to 90% within half a diopter. And that's what makes the change in the game. So you can reach really high numbers of successful cataract surgery cases using Olsen, because his way of calculating the lens position is independent of the eye parameters themselves and makes it available throughout the complete range of eyes from very short to very long ones. And SRKT, Holiday 1, Hofer Q, and also Huygens, they work perfectly fine with average eyes, but they all tend to provide not so good results with extreme eyes. So this all was about the calculation of standard spherical IOL. Now we all know that there's plenty of patients out there that do have some amount of astigmatism. It starts at half a diopter and it goes up to quite high amounts. And a significant number of patients could be treated with a toric IOL, even at lower powers which are available now. But how do we best calculate the IOL power and the cylinder power in these cases? There, Hawk-Stride provides you with a new tool. It's the T-Cone Toric platform featuring iSuite IOL Toric Planner or just the iSuite IOL Toric Planner. So let's have a look first at the T-Cone Toric platform. The T-Cone Toric platform is an add-on to the LensStar Biometrie. It consists of the T-Cone itself, which you see in the image here on the LensStar. It's a cone-like topographer, and the iSuite IOL Toric Planner, which is also available as an independent software tool. Looking at the T-Cone add-on, it provides you with true Placido topography on 11 rings and the 6 mm optical zone of the patient. You get the standard maps, axial map, tangential map, and elevation map. The ISO IOL toric planner, on the other hand, provides you with optimization of the incision location, if you wish to use so, and it allows you to plan your toric intervention on a high-resolution eye image of the patient. So you not only have the sketches you're used to from all the online calculators, but you have the real eye image of the patient, where you see flat steep meridian, you see the incision, you see the implantation axis, and you might even add measurements on anatomical landmarks which might be used intraoperatively for quality check or even for marking themselves. So let's look at the output of the T-cone. As said before, you get the video image of the rings, you get the axial map, tangential map, elevation map. You can also look at them independently with the full color coding scale and so forth. You might now ask, what's the use of topography with toric lenses? Let's have a quick look at the case. That's what you get with a standard measurement from the lens star. So we have all the parameters, axial length, corneal thickness, the anatomic anterior chamber, the ACD from the apex of the cornea to the anterior capsular bag of the lens, the length thickness of the crystalline lens. We have the K readings, flat steep K. We have the astigmatism, white on white. If you look at these parameters, they all look pretty normal. An average eye, 23.4 millimeters, left eye, right eye, same length. Quite a thick cornea, 580, 578 on the left eye. Standard anterior chamber depth, 3.5 millimeters. An average lens thickness, 3.7 millimeters. Looking at the case, we see 43.7, 44.7 at about 80 degrees. Left eye, right eye provide pretty similar results. 1 diopter of astigmatism. Sounds to me like a candidate for a low power toric. So let's have a look at the data a little bit more closely, because when you would do just keratometry, that's what you end up with. You would go to the OR and implant the toric. But since we do have topography, we can go beyond that. That's the topography of the right eye. First we double check, is the axis location okay? So we basically draw the line through the steep axis and we see 80 degree perfectly matches the image. That's good. But we can also have a little look closer to the inferior part on the nasal side of this patient. And there we see that the bow tie pattern which we look for in topography is not fully given. We have some irregularities in the area which is marked by the red circle. Still, I would say right eye, toric IOL is okay. There might be some limitations, but in general it will work. Let's have a look on the left eye. Similar image, but it goes a little bit worse. First double check the axis. Again, if we draw the line to the bow tie, the 80 degrees look very reasonable. But if we look a little bit more closely to the lower slope of the bow tie, we see that the lower slope actually bends away about 10 degrees as compared to the upper slope. And there we already see that implantation of the toric will be a slight compromise, because we can go to the axis from keratometry, the 80 degrees, but this will not match the inferior part of his vision. So there will be some residual astigmatism because of this tilting away of the lower slope of the bow tie, which you can also see in the elevation map. The elevation map doesn't provide a nice rectangular shaped image, but it provides more a banana shaped image. So looking at the topography reveals more qualitative information on how the eye looks like. looking at the keratometry only provides quantitative information, and they combined allow you to judge how well is this patient suited for a toric, and you can then provide him with the best possible information. And in my opinion, that's really crucial, because patients which decide to go for a toric, they're usually a little bit more critical about their outcome. They want to be spectacle independent, and therefore informing them about limitations of the surgery in advance really adds to the outcome. Okay, so let's sum this up. We can double check the orientation of flat steep meridian. We can check the regularity of this astigmatism, and we can also check for irregularities like scars. We'd also be able to see the status after laser vision correction if the patient, for example, doesn't inform us in advance that he used to get LASIK maybe 20, 25 years ago. He just simply forgot about that. And we can even look at keratoconus, but as said before, you only see the central 6 millimeters, so if you have a keratoconus suspect, you might see it at the lower edge of topography, and then you would go and ask for a fully scaled topography to double check the keratoconus status. Okay. Now, when we do have the topography there, we do have the K readings, we have the axial length, we can go to the planning step, and that's how the iSuite IOL toric planner looks like. On the right hand side, we basically have the summary you're used to from all online calculators. You have a sketch with the eye providing information on implantation axis, flat steep meridian, location of the cut, and on the left side you now see the real eye image of the patient. This is done without the T-code. So we have flat steep meridian, we do have the axis of implantation of the implant, and the nice additional thing which we can do is basically we can measure where are anatomic landmarks. Here we have this yellow line at 155 degrees. We see the junction down here. And we could use this information for intraoperative marking, for example, taking a Mendes gauge, dialing in minus 30 degrees basically, and then marking the horizontal line based on this anatomic landmark. Doing so, we know that everything we mark from then on is going to be spot on with what we measured. The reason for that is simple. The image you get here is registered with the data displayed on it. So all data available on display perfectly matches with the anatomic landmarks, and this is an additional value for you in the OR. If we do topography, actually we can double check in the image if the slope really matches. So you see here we can have an overlay of the central 6 millimeter topography. You can also make it semi-transparent. We see that here again the steep axis matches nicely with the bow tie pattern. That's a real nice case of regular astigmatism. We have the calculation of the IOL axis. We see the incision, and here the incision is always optimized, so it asks for incision at 115 degrees in this case. What's done with iSuite is that it calculates where shall I move the incision based on your input on your surgical induced astigmatism to get the best toric outcome. So it basically minimizes the residual astigmatism to zero, so it makes that the corneal astigmatism measured plus the surgical induced astigmatism are matching the toric implant. Alternatively, you can also tell iSuite to provide the incision always at a fixed location, either superior or temporal, whatever is your preference. And if you actually go for an optimized incision, you tell iSuite the range you're comfortable to cut in. For example, if you say, I'm comfortable to cut from 80 degrees to 180 on a right eye, so from superior to temporal, you can teach iSuite that's the area I'm happy to cut in, and then you get, like in the example here, the output that the best result may be achieved if you cut at 115 degrees. Now let's have a look how the IOL is calculated. There we are right now using the Barrett formula because we think it's really providing the best in class results. But how does Barrett differ from all the other approaches which are available there, which are online, like the Alcon toric calculator, like the AMO calculator, or other calculators like the Holiday 2 toric calculator? Okay, first of all we look what does Barrett do in his formula. Barrett's toric calculator is based on his universal 2 formula, which has been there for quite some time. The universal 2 is then applied to first of all calculate the lens position and use this lens position to calculate the power of the cylinder of the IOL in the corneal plane. As compared to the Alcon calculator, for example, that's a big difference because the Alcon calculator always uses a fixed ratio from the IOL implant to the cornea. Secondly, Barrett is calculating the back surface of the eye, the back corneal surface, based on anterior measurements. He's using there a very sophisticated eye model, and this is what makes the winner here. We'll see it in some study data later on. And last but not least, he's using thick lens considerations, so if you have a very low power IOL, he takes into account that usually the design switches from a biconvex lens design to a meniscus design. Okay, let's go a little bit more in depth. So, the Barrett formula calculates the lens position based on axial length K reading ACD, length thickness white to white, IOL power and design. So he's using an eye model. He splits the eye into the anterior portion, which is basically made by the cornea, and the globe of the eye. He fits 2 circles into those 2 anatomic structures, and where they intersect, that's his calculated AC. That's the Barrett formula's anterior chamber. He then adds the correction, the lens factor, which is dependent on the anatomic measurements as well as on the lens power and IOL design. That's his lens position. With this 2 circular approach, he also gets the diameter of the ciliary body. And this information is now used in toric calculations to first of all calculate the diameter of the ciliary body horizontally, or if you have a regular astigmatism in the horizontal plane, and if you have a normal with the rule, the vertical as well. If you have an oblique astigmatism, it will calculate in the 2 major axes of the astigmatism. This information is then used to calculate the back surface of the cornea. And from the back surface of the cornea, we already know from the old days back to Chaval that the horizontal diameter of the cornea on the back surface is always larger, so flatter than the vertical. And that's basically what we know as Chaval's rules. Back in 1890, he already published data that showed that the posterior cornea always adds about half a diopter of against rule astigmatism. And this has been actually proven again in data published by Doug Koch and Li Wang just recently. What they did is they analyzed corneal astigmatism with the pentacam. On the left side we see the anterior corneal astigmatism, on the right side the posterior corneal astigmatism. What the left side shows is that on the anterior cornea we have a strong dependence on what kind of astigmatism we experience based on age. In early years, patients tend to show visceral astigmatism, but the older they get, the more against the rule astigmatisms we see. So we see that the red bars are declining with age as compared to the green bars, which are rising. The oblique astigmatism, they are more or less constant. On the other hand, we have the posterior cornea, and there we don't see this effect at all. So the posterior cornea is always with the steep meridian vertical and doesn't show an age dependence. And that's exactly what Barrett is using in his toric calculator to then design an eye model of the posterior cornea based on anterior measurements. So let's have a look how this turns out in the real world. We have here two studies published by Graham Barrett at last year's ESCRS. The first one is a comparison of the outcome of the toric online calculator as compared to the Barrett formulae using LenStar data. What we first of all see is that with the outcome calculator we only get about 25% of the patients within half a diopter of residual astigmatism. And if we draw the residual change as a vector, we see we have 0.6 diopter offset, which is quite big. Now, if we add posterior information to the image, so we use pentacam measurements for the total corneal power, we can get a better image. That's basically the target you see on the lower left. There you see that we can improve the number of patients within half a diopter of residual astigmatism to about 44%. So we can double them. But still we have a residual remaining error of 0.33 diopters. So this error could only be cut in half using measured posterior cornea. Now if we apply the Baylor toric monogram from the data I just showed you in the previous slide, we can again get a better result. So we can reduce the centroid to 0.2 diopters and increase the number of patients within half a diopter of residual astigmatism to more than 50%. Now you might wonder, why is a fixed number used to adjust for the posterior cornea better than the measurements done by the pentacam? I mean, I don't know the real answer, but I can only assume an answer. If you look at topographers, we all know that they are perfectly good imaging devices. So they provide very valuable and good information on the corneal topography. So we see if we do have local dents, if we do have steepening, if we do have keratoconus, if we do have irregularities. But if we then go to real numbers, they tend to be limited. When you do a little test on your topographers and try to make a measurement a little bit off-center on a spherical eye, and you will realize that suddenly the eye looks astigmatic. And I guess that's the reason why we have this improvement with a fixed number as compared to measured numbers, because using the measurement seems to be a little noisy. Now, going back to Barrett. Barrett not only uses a fixed number to calculate the posterior cornea, but he adjusts it based on the anterior measured cornea. And if you look now here at his results, the same patient cohort, we could go to more than 60% within half a diopters and look at his centroid. So in average, he nails the result. 0.06 diopters, it's really spot on. So now, some of you might tell, well, that's not a fair comparison because we all know of the limitation of the Alcon toric calculator. No, it doesn't take into account the lens position. So he did a comparison against the Holiday IOL Consultant toric calculator. And this calculator actually takes lens position into account. And if you look at this result, so that's the top left target we see there, we see that we have a slight improvement as compared to the Alcon calculator, but it's not significant. We have about 28% of the patients within half a diopter, and we still have a centroid of about 0.5 diopters, which is still significant. The image looks very similar if we now add the posterior corneal measurement from the pentacam. We can improve the results, so we can go down to a centroid of about 0.3 diopters and have more than 35% of the patients within half a diopters. But the game changer is not done by the measured posterior cornea, but by applying the Barrett formulae, because there we see we can basically double the numbers within half a diopters, so we have more than 70% within half a diopters, and we have the centroid spot on. So again, you might say, well, Graham did develop the formula and he shows it's working well. That's what I would expect. And that's why I would like to show you some independent data from the Angtal Eye Center in Tel Aviv by Adi Abulafaya. And he basically did the same thing. He plotted the centroid of the Barrett toric calculator against the standard calculator. Here he did it on the SN6AT from Alcon. And what we see here is that his data basically matches what I just showed you in the different slides. We have a centroid of about 0.5 diopters for the standard calculator, and for Barrett the result is nailed spot on. If we look at the result from the Barrett calculator as compared to pentacam measurements with the toric standard calculator, we see again the same thing, about 0.4 diopter of the centroid with the standard calculator and pentacam, and Barrett is spot on. And last but not least, I would like to go to this slide. Some of you might say, well, I do have an IOL master. I can take the IOL master measurement, go to either the ASCRS or the APACRS website and use the Barrett toric calculator there. But still you will get a difference between the LensStar and the IOL master. If you look here at the centroid, they are equivalent. They both are spot on. But if we look at the spread, you see that the LensStar's results are much tighter together. So with the LensStar, you get more patients really happy because you will have less outliers. And if we look at the 95% confidence interval, it's the ellipse you see on the left and the right side, it's about half a diopter where the LensStar is better than the IOL Master. And this study was done with IOL Master 500, so one of the latest models they have. So let's sum it up. With the LensStar T-Con toric platform, we can provide you with highly accurate K readings. We can improve the confidence using topography to check the axis orientation and the regularity of the astigmatism. The Barrett toric calculator, as shown with just the recent results, is the best-in-class IOL prediction method. Using LensStar Biometrie, you get the best possible prediction result available, and all of it in a very smooth and safe workflow. If you want to do the same thing online, you always have the possibility of data transcription errors and so forth. And last but not least, you can plan your toric intervention on the real eye image of the patient. You can add anatomic landmarks. This all helps to double check your outcome. Also here you're going to get access to a PDF file on the toric planner as well as the T-cone, and to an addendum to the Cataract Refractive Surgery Today magazine, which was published in October last year. That's all going to be tomorrow on www.ootech.nl. And again, if you go to the Hawkstride website, you can have a look at the lunchtime seminar of last year's ESCRS. There you find talks of Barrett and of Olsen. So, thank you very much for your time, and feel free to ask questions. I'll try to answer them the best I can. Thank you very much.
I think everything's
Okay.
I think everything is clear, Thomas. Thank you very much for your presentation. Iedereen heel erg bedankt voor uw deelname. Zoals eerder genoemd is deze webinar ook te bekijken op www.ootech.nl en dat zal vanaf morgen zijn. Mochten er nog vragen binnenschieten, dan kunt u die ongetwijfeld ook bij ons vragen. Namelijk, u kunt ze sturen naar ootech@ootech.nl. Wij zullen zorgen dat uw vraag beantwoord wordt. Bedankt voor uw deelname en tot binnenkort. Dag.